what I want to tell you about today is really about thinking about how we extend this idea of workflows into laboratory practice, into the experimental world. And so I do have to admit there's really no exascale computing in this problem. But I want to tell you about a little adventure that I've been on over the last few years and the work that we've been doing really to try to think about how we might adopt these types of best workflow practices in an experimental setting. And so I'm going to use the pronoun we throughout this. It's not just because I have an idiosyncratic pronoun choice, but rather that this is really a team effort and largely work together with really the experimental brains of the project, Alexander Norquist at Harvard College and Emery Chan at the Molecular Foundry at LBL, who's our real lab automation guru. Assisting, I'll tell you a little bit about some of the experimental work, just so you have a setting of the challenge. But assisting in the experimental work have been a number of technicians over the years, many of whom have gone off and graduated from other places. Also some postdocs. Color-coded in red are the ones that have worked on software parts of the problem, and color-coded in blue, the ones that have worked on the experimental side of the problem. And a number of master's and undergraduate and even high school students over the years that have participated. So really it is a team effort. So what's the problem? Well, we heard this morning in Claudia's talk about the challenge of halide perovskites and how remarkable they are as materials. You can use them to make neat gadgets like solar cells and X-ray detectors and so on. And at the same time, all the challenges that are inherent in trying to calculate properties of these materials and understand what's going on. And so what is really appealing about this type of material as a test bed for exploring experimental workflows and autonomous experimentation is the way in which they're kind of modular, right? They have these different pieces. And so our archetypal halide perovskite material is shown on the left, this methylammonium lead iodide. It's got an organic building unit, this little methylammonium cation. We usually just refer to them as amines, so if there are any organic chemists in the audience, don't be too scandalized. And then it's surrounded by inorganic building units. The gray spheres representing lead atoms here, and the purple spheres, various halide ions. And so really, we can think about this as kind of being a modular system in the sense that, at least in principle, we could imagine swapping out those organic building units and going to our favorite chemical supplier catalog, having a choice of tens of millions of different organic molecules, and then fitting it into the structure. And we might achieve radically different structures and in turn, radically different properties for these materials. And there's just kind of a vast space of these things that we can find. So that sounds like a great idea, right? Except it's not quite as easy as Legos, right? The real challenge is that we actually have to make this stuff in the laboratory. And that really involves a trial and error process. For a given choice of the inorganic Lego units and a choice of what the organic Lego units are, we've got to decide how much of them we want and what those relative ratios should be, their concentrations. We might have different additives, acids, small molecule additives that might be added in very trace amounts up to maybe even 10 mole% amounts. And then there's some set of processing that we have to do in order to actually cause the reaction to occur. This may involve heating and mixing steps and so forth, right? And so, you could try to estimate how many different conditions there are. This was one estimate that one person in the group came up with of like 10 to the 7, but whatever it is, it's just sort of an absurd amount. Certainly something that we can't do practically in the real world. And so, I think what's really kind of interesting about this problem is that it's got aspects of a kind of a continuous optimization problem, right? Varying all these compositions, but it's also got discrete aspects as well, right? Like what's the choice of these individual building units? And, you might just ask, well, why don't we just compute this? Well, I think, as we heard in Claudia's talk this morning, there are a lot of real difficult challenges with these materials. And so computing their properties is tremendously difficult to do from first principles theory. Computing the synthesis pathway and the assembly of these materials, I would argue, is equally, if perhaps not even more challenging, right? These are held together by a vast array of non-covalent interactions, all of which are very subtle and very easy to get wrong. And we're interested in sort of the kinetic processes that allow us to grow large, high-quality single crystals. So, all right, we can't use physical theory. Why don't we just bring out the hammer of machine learning and try to solve it through machine learning? Well, it turns out that's also not as easy as you might think it would be, for a few reasons, right? One of the things that we found is that if you want to build machine learning models that predict experimental success and failure, that maybe take in some recipes that you have and predict what the outcome will be of that recipe, you really need experimental data about both the successes and the failures in the laboratory. And of course, if you've opened up your latest issue of Journal of the American Chemical Society, for the most part, the journals just publish a single successful result. So they don't publish all of the marginal successes. They certainly don't publish the failures, right? And so I'm always jealous of the astrophysicists. They have these great things like dark matter and dark energy. And so I like to refer to these as the dark reactions, right? Or the dark data. But really just think about it as all those unreported experimental details. Now, the thing is laboratory scientists are actually pretty careful, right? They do write these things down in laboratory notebooks. And we heard, also earlier today, right, about, ways in which, there are concerns about privacy and ways of collecting those into other things. And so actually what we did now a few years ago was we said, we've got all these old laboratory notebooks on a shelf. We're just going to pay a couple undergraduate students to go through and digitize a decade's worth of old laboratory notebooks. And then with that data, we could build very simple machine learning models that were just as good, if not better, than human experts at predicting reaction outcomes. So, we then had to test this. So we paid another group of undergraduate students to run hundreds of experiments in the laboratory to build up statistically valid sets. But what was really kind of encouraging to us was this idea that somehow there's a missing piece of the data, right? And so if we had some mechanism of collecting these failed reactions and having that comprehensive data set, there could really be a lot of value for experimental laboratory scientists. And maybe you can even learn something from your model. But that's a story for another day. Now, it turns out that's even not quite enough, right? One of the things that we found as we analyzed this data set of reactions in old laboratory notebooks or even published reactions is that there are tremendous biases in the types of reactions that experimental materials scientists try. You can look at this in a few different ways, right? I mean, one way is to look at the types of organic building units that people use in making compounds like these that are in reported structures in the Cambridge Structure Database. There are thousands of them that are out there. And it turns out that some of the reagents are used in just kind of a disproportionate number of the reactions that we see. And some of them are hardly used at all, right? In fact, actually, you can kind of quantify this. And something like 18% of the most popular 18% of these organic building units comprise, 82% of the of reported structures, right? So that seems kind of weird. We found similar things in the choices of reaction conditions in the laboratory notebooks. And maybe that's not surprising, right? I reflux the reaction for 24 hours. You never see 23 and a half hours, 22 hours, 25 and 3/4 hours. Similarly to the way that if you look at recipes in a cookbook, they set the oven at 350 degrees Celsius, right? But maybe there's a more optimal choice of 342 degrees Fahrenheit or whatever, right? So maybe there are some reasons why people do this. But there could be genuinely good reasons that these biases exist. So what we did is we again paid a bunch of undergraduate students to run hundreds, 500 or 600 randomly generated experiment plans with a variety of different organic building units. Things that were popular, right, that showed up in this disproportionately represented set. Things that were unpopular, right, that had just been used in a small amount. And things that you could buy cheaply from common chemical vendors, but had never appeared in the Cambridge Structure Database. And what we found is that it actually makes no difference, right? The popular versus the unpopular. You could perform a randomly generated reaction, and you're just as likely to make a high-quality crystalline product. And similarly, if you randomly sample over reaction conditions like pH, concentrations, temperatures, and so forth, again, your probability of finding this with some other choice, was kind of just about the same, right? So this popularity really was uncorrelated to the reaction success rates, the cost, and the technical considerations. In other words, there was just no good reason for it. Humans were just stuck in a rut, right? And you might say, well, that's an interesting observation. Why should we care about this as machine learners? And what we found is that actually, if you had a data set that was just randomly generated experiment plans, with the real outcomes, you could use a much smaller data set, perhaps 20% smaller, and the machine learning models that you trained were better than the human-generated data sets by all metrics that you looked at. So, in some sense, this human insight or this human intuition actually maybe is steering us wrong, right? And we might want to think about removing that, or certainly just kind of keep that in mind as we go forward. So I've told you about some problems. This would be a very boring talk if I didn't tell you about some solutions, right? And maybe a solution that we heard alluded to in Marcus's talk earlier this morning is this idea of autonomous research labs or closed-loop labs. And we'll hear more about that later this afternoon from some of the talks. But the idea might be, I could have robots that do the synthesis and the characterization, maybe even dispatch simulations, according to some of the workflow management tools that we've heard about in the past few days. And then, I'll shuttle that data off to some data archive, like the ones that we heard about this morning, to algorithms that will kind of analyze it and summarize what's going on, and then have some decision-making algorithm that will decide what the next experiment should be, right? And maybe that's a way that we can, get this comprehensive data set and also eliminate some of the influences of human choices that are steering us wrong, right? So that's at least one idea that's been posited. And I guess what I'd like to say is, often this is sold as this vision of, we're just going to set up the robots, and then we'll go home, and then we'll come back next week, and all the results will be there, and it'll even have typed up the paper for us. I actually don't think that that's really the value of systems like this. I think really the immediate value, right, and maybe kind of the more important value, is that it's really going to be a kind of a technology that helps us improve the reproducibility and replicability of experimental science. So just in the same way, as we were hearing yesterday in the pi iron talks, right, about how by defining this sort of well-defined schema and way of thinking about setting up a set of computational experiments, a new student could go back and repeat what that process was. I think this type of automated experimentation will help laboratory scientists do that as well, right? Because for one thing, it requires a complete disclosure of the laboratory process, right? You've got to tell the machine exactly what to do, and now you've got a record of what that was. You can share those records across different laboratories. And so, you can try to replicate the results, not reproduce the results because the outcomes will be slightly different because of randomness in the lab, but replicate the results. Of course, it'll generate this complete record of successes and failures that we need. Maybe it's also technology for reducing the sampling biases. And, if we have this comprehensive capture of data, then we might even be able to apply tools from statistics to try to learn from things that seemed insignificant at the time, right? Like, in other words, we might be able to automate serendipity. And I'll tell you a little bit about that later on. That being said, automation really does not solve all of our problems. And in fact, actually, there exists, and I think there will remain a need to capture the operations that human actors have, right? A technician preparing a stock solution. We need to capture that information that occurs before it gets placed onto the robot deck, right? I think another thing too, while this vision of a completely self-driving laboratory where everything gets shuttled from one instrument to another is very appealing, I think that certainly there's a lot of legacy non-automated equipment that exists, right? And that has unique capabilities. And so we also need some way of importing data from these capabilities and exporting experiment plans to those capabilities. And so, really, if you asked me to make a prediction, my prediction would be that, we're probably going to see more of a model of islands of automation, right? Laboratory scientists will say, there's some really tedious step that I have to perform. Let me just automate that. And everything around that will involve human operators, right? And so, while it's easy to get distracted by robots and gadgets, and I'm certainly guilty of being distracted in that way, it's certainly not the only story. And so, if we think about trying to capture this workflow, right, that has aspects of automation, that has aspects of human workers performing processes, and that has to serve these discovery needs, we just want to keep this in mind. So, for an audience like this, maybe we don't need to. Yes, sir.
So how would you define automation here? I mean, is it AI-driven automation? It's more like expert systems.
Yeah, that's a good question. I mean, it's undefined, probably for good reason, because I think there are lots of different definitions that you could have. I mean, I'm even willing to accept a very low definition of automation that might even just mean blindly doing the same thing repeatedly, right? I mean, that's probably like kind of a very near-term realistic goal, right? And this kind of autonomous, right?
Yeah. Because there is
much harder, right?
Automated and autonomous.
That's right. That's right. Okay, so all of this calls for something, right? There's a need, right? Whether we have machine learning algorithms that are kind of providing an input, or just very smart people thinking about things, having dreams, doing DFT calculations. Somehow we need to turn those ideas into an action in the laboratory, right? And from that action in the laboratory, we need to get data out, right? And kind of feed that back into our analytic process. And those experiment plans that we generate somehow have to be reduced to a proper set of instructions that we could dispatch to a person in one laboratory, or maybe dispatch to multiple laboratories to perform, right? And so, I think really the goal of experimental workflow management software is to try to deal with these challenges, right? Doing things in the lab might involve robots, it might involve humans, it might be kind of messy, but there's a role for software to try to kind of capture these specifications of experiments, reduce them into a form such that the robots and humans can perform them, and then manage and manipulate that data, right? Kind of get it into a form such that it can be used by other workers, right? And so really our goal in trying to develop some experimental workflow software was not to deal with the machine learning algorithms, right? Because there are very smart people working on that problem, but really just to kind of deal with this blue semicircular region. Okay, so we tried to put together the pieces of the puzzle and kind of see how this would work, right? And part of the reason why we had this large team was that we wanted to show all of these pieces playing together. So we needed to work on automating the experiments, right? And to do this, we developed a system called Rapid, right? And we've demonstrated that in the context of a few different synthesis methodologies for perovskites. There's also this need to develop a workflow for managing the data, right? And so our workflow software that we've developed is called Escalate for experiment specification, capture, and lab automation technology environment. And I'll tell you a lot of details about that. And then finally, we really needed to stress test this and see that it actually did something useful in the lab. So we use this as a platform for benchmarking automation versus traditional ways of doing things. Algorithmically driven experiments versus random sampling. Different algorithms versus other algorithms. And I'll tell you just about a few examples of testing it in the laboratory. Okay. So, just as kind of a motivation then, right? We wanted to automate the experiments. And again, keeping with this idea of automation but not autonomy, we were sort of constrained in this project to just work with commercial, off-the-shelf robotic liquid handlers, right? Like the one shown here. It sounds really fancy. It's really just a fancy set of pipette tips. Or, you can think about it as being computer-controlled straws, right? That can slurp up some liquid right over here, right? And draw it out of these sample wells, and then dispense it into some glass vials on the other side. And these glass vials can be heated to 100 degrees Celsius. They can be shaken and mixed. And then, of course, we can kind of do things with the samples that get formed, right? Here are some Perovskite crystals in the bottom of these samples, right? And so, we wanted to show that you could kind of do this with a variety of different chemistries. We looked at a few, and just to kind of create the illusion of realism, one was this inverse temperature crystallization, which is just thermodynamically really interesting and neat. We also looked at an anti-solvent vapor diffusion method. There are pros and cons and kind of different chemistries that one can access here. But really what we wanted to do was also kind of explore a diverse set of chemical systems, right? Lead halides with just a single organic building unit as the Lego. Things called Redelston-Popper phases that have multiple organic cations and different ratios. Copper halides, and so on. And we don't just want to make stuff, we want to characterize it too. And so over the course of the project, we developed some automated characterization tools so that we can characterize the samples that we make, by things like powder X-ray diffraction, optical imaging, aka just take a picture of what the crystals look like, and also some simple spectroscopy, absorption and fluorescence spectroscopy. And really kind of a lot of the challenge in this, and I have to hand it to the postdocs that worked on this, is they really needed to sort of minimize the role of human operators. There are a lot of really challenging sample handling processes that they need to do, and they need to keep up with the rate that we did reactions, right? And so, which is on the order of like 100 experiments per 5 hours, or maybe some longer time experiments as well. We also had some fun. Those of you that work on perovskites are aware that there's this tremendous problem. We want to use them as solar energy materials. They're not stable when exposed to light. That's kind of a problem. They're also not stable when they're exposed to heat or moisture, right? So we built this accelerated sample chamber that we like to refer to as the artificial Singapore. It exposes the samples to 86% humidity, 1.5 sols of illumination, and 85 degrees Celsius, right? But embedded into this chamber is also a computer vision system, basically just a camera. And what we can do is essentially just watch the samples over time. As they degrade, they undergo phase changes and other things, and there's a color change associated with that. So we can actually just do some unsupervised clustering and then figure out the kinetics of the process, basically by watching the area of the color changes. And all of the hardware is open source. We had just a really smart student who was a good hacker and knew how to put all these things together. So that's just kind of another characterization that we have. So I've told you about the robots and things like that. Let's get to the meat of the problem, which is the software. The real challenge then, as I've kind of built this up, is we've actually got kind of a complicated set of data that we've got to manage, right? We've got the experiment plans that describe compositions and procedures. We've got some samples that we've made, right? Things like images of the sample, spectra of different kinds. And so how do we organize this in some systematic way that also is maybe generalizable, right? We don't want to have to rebuild this system for every new type of experiment that we're doing. And so that's where we tried to develop this Escalate software, right? And so the idea was that we really wanted to provide an abstraction layer or an API for specifying the experiments that a human or a robot or whatever would do. Generate instructions as needed, and then not only capture the data, but also automate some of the process of adding descriptive features onto that data, right? Because, if you think about it, the brute facts of the laboratory are usually not insightful, right? Any of you that have taken a high school chemistry lab, right, probably remember, just knowing the masses of things that you put in, right, those brute experimental facts is not nearly as formative as knowing something like the mole ratio, right? And so there's a little calculation that needs to be performed in order to kind of figure out that stoichiometric information, right? And of course, there's also this vast toolbox of cheminformatics that people have developed in the pharmaceutical industry, right? That give us descriptions of organic molecules that we can build on, right? And we also heard in the talk this morning the importance of fair data and data reporting standards. So if we can kind of make that a little bit easier to do, that would be really great. Right? So that's really kind of our goal here. And I'm going to walk you through that process right now. So we started off by really just kind of sitting down and thinking about how would you describe an experiment? And it turns out there's not much that you need to describe an experiment, at least in kind of the most general terms, right? Experiments are performed by some entity, right? A person, at some location. The type of experiment, might be defined. But, really kind of some of the key things are materials and actions, right? And so you could think about, a laboratory process as consisting of a set of materials that come into an action that is taken on them. And then that action generates some daughter material, right? Something that comes out. As you perform these actions, some of the actions have outcomes or observations. In this kind of early data model, we separated those into observations are things that humans do, right? Where you have to ask a human, and outcomes are things that instruments make. But maybe even that distinction is not necessary. One of the things that we thought was really important is also like this idea of what makes an experiment the same type of experiment. Right? Like, in other words, how should I judge the similarity of a group of reactions together? And so, a way that we thought about doing this was this idea of defining kind of like different levels of specificity for describing an experiment, right? We could think about a template as being sort of like a general description of what an experiment should be, right? Just in the same way that if I was describing how to make a cocktail, right? I would say, well, there's a vast family of cocktails, and they involve, 2 parts of some spirit, they involve 1 part of vermouth, and they involve a garnish, right? Without necessarily specifying what the specific ingredients are, right? Which particular ones I'm using. So we called that a template, right? The other thing that you have is that then you say, all right, well, now I'm going to make a very specific cocktail, right? I'm going to make a Manhattan, let's say, right? And that's going to be 2 parts of a specific bourbon. It's going to be, 1 part of sweet vermouth, and I'll put a maraschino cherry in there, dash of bitters, right? So that's really kind of a specific description of what that cocktail should be, what my intent is for you to go forward and make it. Now, actually, the thing that you do in the lab or at the bar is probably not exactly that ideal specification, right? In other words, the model establishes the intent of, what do we intend to perform in the laboratory? But then there's an actual physical occurrence in the laboratory. And to the extent that we know deviations of what actually happened in the laboratory from what our intent was, we want to capture that as well, right? So we call that the model and the object, right? That's kind of not the best words. It's probably overlapping in your mind with object-oriented programming. We really just couldn't come up with better ideas, right? But the important thing to see is that as we move from general to specific, right? Like the general template maybe just describes a whole class of things, right? So in other words, it has type information. The model, involves particular types of materials and actions that perform, and we only really add the observations and outcomes, when we do the thing in the real world. All right. So, you can think about the templates as containing information that constrains what's a feasible experiment. Like if I'm mixing liquids, there's some convex combinations that are allowed and some that are not, right? But you could also incorporate instrument limitations into the idea of the template constraints. The models, right, are these notional experiment plans, right? So what are the materials that you should be using, right, and actions that you should be performing, and what are the observations that you should be doing later on? And we actually wanted to try to kind of set the default practice to move people away from getting stuck in a rut, right? And so by default, any free numerical parameters are just sampled, over their feasible ranges and assigned to random locations in the experiment. So, if you want to do something very specific, or you have a particular kind of line of experiments that you want to enumerate, you can do that. But, by default, we just want you to kind of just do things randomly. It might be better than doing things in another way. and then, of course, there's the question of how do you interact with the human operators and the robots, right? So we kind of have been developing this over a bunch of years, right? Our kind of like first version of this, which we paradoxically called version 2, was kind of used some web-based forms where we essentially just hacked Google Sheets to serve as a front end, and then had it spitting out JSON files, behind the scenes. But that really wasn't what we wanted to do, and so we kind of learned from this process. And our focus in kind of the current version, right, version 3, right, is really on was really focused with a kind of a prime attention on machines, right? So we started actually developing a REST API and then built a graphical web interface on top of that, right? So I just want to kind of walk you through some of the interactions just to kind of get the flavor of this. There's a full tutorial in the form of an IPython notebook that you can find on our GitHub website that kind of walks you through in probably a much more pedagogical way than I'll be able to do in the next 20 minutes. And then, there's also a really comprehensive user guide to the graphical users interface, right? Also on the GitHub, right? So, we talked about materials, right? You might have a library of materials that your laboratory has already defined. And so it's easy to just query those, right? We're just using the simple HTTP wrapper, around this REST call, right? But you get out some kind of structured list of materials that are in your lab. And materials that are organic molecules that have a defined organic structure, we can actually automatically calculate cheminformatics properties of those. But there are other types of materials that maybe are like some solid sorbent, right? And so there are other types of properties that might be defined by a vendor, like minimum and maximum mesh sizes and cross-linkage percentages for polymers. It's also possible to define arbitrary properties that get associated with these materials and can be propagated down to the analysis pathway. And so you can look those up. Obviously, there's kind of a web-based version of this that looks nicer and allows you to kind of search for things and kind of relate your information to other public databases. The workflows are our way that we organize action and material relationships, right? And so, you can think about a workflow as being kind of the graph, right, of like what happens to a set of materials. How do they come in? How do they walk through a set of actions in their lifetime? And so, this is just kind of pulling up, one of these action material relationship graphs. But in the web-based version, we actually have this drag and drop interactive piece that allows you to connect them, right? So you essentially, kind of add an action, right? That's one of these boxes here. And then you just click and drag to draw an arrow that shows where particular materials are coming into or out of the action, right? And one of the things that we have is we have a library of default action definitions. The common stuff like dispensing liquids and heating things and shaking things. Everything you need to make a martini, right? But you can and actually one of the nice things with the default action definitions is, you can also add other attributes. So a lot of these ideas are really common, and there are other types of descriptions of experimental workflows, things like KDL from Lee Cronin, right? They map onto these ideas just with a different name, right? So you can just add that synonym, and we've used that to import or export to KDL, for example. But if you have some other action that you want to perform, you can always just define your own action definition, right? And again, that's something that you could do in the web. And once you define that, what an action is, you just get to use it, and everyone in your lab gets to use it going forward, right? Those actions can also contain what we call e-documents, right? And those could be scripts or those could be files that are things that you want executed on the machine, right? Or that perform some calculation that is needed in order to generate a file for the machine. And so then, when we go to perform a new experiment, right? Those objects are really kind of just instances of a workflow, right? So we say, create a new experiment that is an instance of one of the workflows that we've defined, right? And again, you could just do that through the web. And when you go forward and do that, and you specify, how do I want to generate my experiments and so on, it gets added to an experimental queue, right? And so then, in your specification of the experiment, you could say what lab you want to perform this, or if there's a particular person that you'd like to perform it on. And so all of the users in that experimental queue, can then look at the jobs that they're allowed to do, And then when they feel like they have nothing better to do, they're done wasting time looking at cat videos, they'll kind of log on and say, all right, great, what's in my experimental queue? Let me start this new experiment, right? And so this gives us a whole set of kind of instructions for the user. It says, okay, great, you're about to start this. Maybe here are some files that you should load onto the robot. Here's some post-processing that you're going to need to do. And then, walks them through the procedures that they need to perform. Now, this web form is super ugly. We really don't know anything about modern web design. But, everything on this form was automatically created from the workflow that we specified, right? So it said, hey, what is it that you should be doing? What did you actually do? How much did you actually set up? And all of these have sort of units associated with them and so forth. So it's pretty ugly, but it's the best we could do. And so then, as the user is going through and filling this in, they fill in, what are the actual values that they performed. As they kind of encounter things where they need to maybe grab a file from the robot, they're prompted to kind of upload the file, and then that gets associated with this particular experiment, right? And then everything lives inside of a Squeal database, right? And so it's all there, and you can query it and try to find out, what happened in the experiments in the past, right? Or find out what's the status of an experiment that I put on the queue, and when it's done, retrieve the results. Now, of course, just having this REST API is not so friendly. So we've kind of experimented with building different types of tools for looking at the data. I mean, one little experiment that we did was creating this live web dashboard. And so every time new experiments were performed, it would just kind of go through and kick off training a bunch of machine learning models, just basic little models, featureize the data, and just provide some oversight. So you could browse through and see how this works. We used to have it running at the Texas Advanced Computing Center, but since this project ended, we no longer have that account. So there's no live way that you can see this demo that I'm showing you on the screen, but the code is posted online. The other thing, and actually the part that we decided to keep and focus on was, in a lot of use cases, you want to export some tabular form of all of this data. So you need some way of reducing all those observations into tabular data. And so really, that's kind of what we focused on. For the organic molecules, it's possible to featureize them. And we built a package that we call ChemDescriptor that basically just allows you to talk to RDKit or ChemAxon or Mordred and pull out different fingerprint values and associate them with your data. And we also kind of developed a little calculator module that does safe evaluation of arbitrary numerical calculations using your data, right? Because we wanted this to be something where users could just say, here's a calculation that I want to perform, but we don't just want to do a string evaluation on that for security reasons, right? But the other thing that we thought was really a valuable use case was just kind of making it easy to dump this data, right? And so if you do an experiment campaign, it should be really easy to just export your data. And so we developed some canned Jupyter Notebook binder type export features that will just take a set of experiments that you performed and give you this interactive browser where you can kind of click on each point. You can see maybe a photograph of what happened, color code the results by their feature, correlate it to other data like infrared camera images of the heating plate, but also any of the spectra that are associated. And so again, those of you that were here yesterday, we heard talk about using MyBinder. This is just another example of using that to try to create something that you might include as kind of an extended form of supporting information online. Okay. So you go through all of this, and then you say, so what? Like, why is this useful, right? So I want to just kind of quickly show you a few things of kind of uses where kind of having this comprehensive data capture or having this type of workflow really allowed us to do something neat, right? So one of the things that you might say is, if I look at this infrared image of the heating plate, there are some variations in temperature along the edges. It's a little cooler on the edges. Does that make a difference? Right? Well, if you collect thousands of experiments, you can start to pull out statistical information about how reaction outcomes vary if you're at these slightly cooler or hotter positions, and even try to relate the effect to particular organic building units, right? And so, that's kind of fun. You can crunch some numbers and see what happens. Maybe there's even a way that you could think about, just sort of building very small machine learning models on batches of experiments and using the discrepancy between the predictions of one machine learning model and another machine learning model to identify anomalous experiments. But actually, a really nice use case that we had is something that we've been calling automated serendipity, right? There are a lot of ways in which our experiment is really crude, right? We don't perform these reactions in a glove box, and yet things like humidity and variations in laboratory temperature, can actually have a meaningful impact on the reaction outcome. So while we don't control these variables, it's really easy to measure them, right? And associate that data with every experimental point, right? And so, we could have considered that a limitation, but actually we consider that a benefit, right? These natural fluctuations are kind of like a natural experiment that is being performed, right? And so, if you look at kind of variations in our observed humidities, even inside of an air-conditioned lab, they vary during the year. What we did is we tried to look for, batches of experiments where we use the same set of ingredients on a low humidity day or a high humidity day, and where the distribution of outcomes was different, right? Maybe they were more successful on high humidity days or more successful on low humidity days. And, you could just use some really basic statistic models to say, that seems like an outlier point, right? That's maybe a more promising place for us to look. So, we kind of view this as a way of prioritizing the most interesting experiments to explore, right? And so, you can kind of combine this experimental sloppiness with comprehensive data capture to maybe help you discover something that you didn't know. So we find the discrepant batches, right? Prioritize the ones where the effect is biggest. You can then set up the robot to do deliberate, controlled experiments, right? To test the effect, right? We set this up as paired experiments with and without added water. And using the robot, you can now acquire statistically significant confirmation of the effect. And so, for those of you that are Perovskite nerds like me, we found something really neat where, in this inverse temperature crystallization, water can both promote crystal formation, which was known and kind of consistent with the mechanism, but also we found some cases where it appears to inhibit crystal formation. And we don't really know what the underlying mechanism is yet, but we saw similar trends when we did this in thin films as well. So kind of interesting area, and maybe actually learning something genuine scientifically. The other thing you could do with a platform like this is use it to test your machine learning algorithms, right? Because now we've separated developing the machine learning algorithm and even who is developing the machine learning algorithm from the people performing the algorithms in the lab. So we've looked at kind of lots of different test cases of comparing different things and trying different techniques. I just want to tell you about one that we ran a year ago that was really kind of fun. And it exemplifies things that you can do if you have this type of experimental workflow software. So we called it the Perovskite Challenge competition, also the bake-off. And the idea is that we wanted to invite external teams that would submit algorithms. They'd have access to the data, right, and be able to use their algorithms to specify experiments that they could use to remotely play this game of optimizing reaction conditions, concentrations, and so on, to find the conditions that would allow them to grow a large, high-quality single crystal. And so in the end, we had kind of 11 participants or competitors in this. There were a few places that submitted more than one algorithm. But essentially, the automated experimentation was divvied up between the Molecular Foundry at LBL and Alex Norquist's lab at Haverford College. So there you go, East Coast and West Coast. The experiment plans in ML were done at a number of places, including a few private companies down in Arlington that were participating in this program, and also a company in Lausanne, Switzerland, that has some algorithms for optimizing experiments, and they wanted to see how well they would do. And then all the compute infrastructure was provided at the Texas Advanced Computing Center. So yeah, kind of a cross-national, maybe even international project. And so what does the competition consist of? Well, we wanted to actually do a few rounds of competition. So we looked at 4 of these different organic building units, 4 different types of Legos. And we actually did 2 trials for each of those Legos, right? So 8 trials. Everyone starts with the same 10 randomly selected experiments, right, from the possible experiments that could be performed. So they all start with the same data. Then they can do anything that they want model-wise. They can use all of the historical data that we have on other building units, other ingredients. They can choose to ignore that entirely, right? And they can model this in any way that they like, right? Each competitor is then allowed to request 10 new experiments that they're going to perform in the laboratory. And again, they're free to just sample randomly or use any acquisition policy that they'd like, right? And then at the end of those 10 additional experiments, they then make 10 predictions about how would I grow a large, high-quality single crystal of this new Perovskite, right? And we judge them on that outcome. All right, and so there's kind of a long story here. If you'd like to read about it, we have a paper on the Chem Archive. To summarize things and maybe oversimplify things, the best performance in terms of reliability across these different amine building units and different attempts, cold start attempts, the different trials, different random initializations, high success rate, and so on, tended to be various forms of Gaussian process regression. Again, as we heard this morning, there's a lot of nuance in there. And so I'm glossing over the nuance of the particular kernel methods that were used. There were a variety of different ones. A Bayesian additive regression tree method also did quite well. And what was neat is that the people used different approaches, right? Some of them used side information about chemical properties or historical data. Others did not, right? And so we kind of try to unpack that a little bit. And one of the things that we found was that many of the sort of active learning based algorithms got trapped in local minima, right? Like if they just got lucky early on, then they never really, kind of explored the most diverse set of possibilities. And so we also, in this paper, kind of talk about some model agnostic ways of kind of pushing people apart and framing that as an optimization problem. But, I think that's kind of a sideshow here. Okay. So, just to kind of like wrap things up and summarize, right? I mean, this was a project where we really tried to co-develop the software and the experiments and actually use it for something as we went along. It involved this kind of iterative process, right, of starting just by observing what the experimental teams were doing and what their needs were, trying to kind of build prototypes that help them do things, learning from the limitations of our data structures, and then, ultimately trying to kind of turn those ideas into a full-fledged kind of real database-backed product, with some reasonable way of interacting with it. And so I think with that, I'll just kind of wrap up, right? I mean, I hope I've conveyed to you some of the fun that we've had over the last few years of trying to develop open source software for dealing with these types of hybrid, automated and manual experimentation and providing an abstraction layer for algorithm developers, to do things in the lab. Also, at least, in that bake-off, I've shown you an example of how we were really able to spread out the experimentation across different laboratories. And, the instructions can come from wherever they are in kind of remotely operated. But, we can also split up the work across different labs with different capabilities, kind of demonstrating that we do have some amount of abstraction. And then finally, at least I've hinted at a few of the ways that we've used this capability to benchmark algorithms, right? And, I think the value there is, there are a lot of really smart ML algorithm developers that maybe don't have a buddy who is an experimental lab expert. And so this really kind of allows them to participate and see how their algorithms do on real physical problems. Yeah, by the way, also we've discovered and characterized just a tremendous number of new materials, but that would be a whole nother talk. So I won't give that talk today. And so in the interest of time, maybe I'll just stop there. And I'm happy to take any questions that you have. Thanks.